So in this example, we're going to find the total resistance for this network. To find the resistance for the network, we need to understand the connection between all these resistors. Find the resistor network connection between node A and this node B. So there's no resistor in here, so this is the same node. So this is the same node, this is the same node B, and this is the same node B. So the first thing that I want to find out is are there any direct connection between node A and B? So once it passes one element, this will be a new node. So I'm going to call it a node C. So once that node is called a node C, and this is node C, because these two nodes, they are connected by using a wire, there's no resistor in between. This is one node. And similarly, this is a node C. So we label all the node C's. Are there any branches connected directly between node C and a B? Here, this branch, right? So that is a branch between C and B. So I'm going to put it down here. And one resistor have a resistance of 9K and the other one is 1K. And this resistor on the top between node A and C, that is 24K. Are there any other branches between C and B? No. So this is why we need to define a new node. Let's call this new node D. And if we define this node as D, this will be our node D, because these two nodes, they are connected by using one wire. That is one node. And over here, this is a new node. So let's call that node E. So this is how we label the nodes. We label it according to whether they are new nodes or not. So we already know that there's no direct connection between C and B other than this branch. So we have to go through another node. Let's say it goes through the node D. Let's see the connection goes through C to D, then eventually come to node B. Between C and D, how many branches do we have? C and D, this is C and D, right? We got another C and D there. And these two are in parallel. This point is our node D. So between D and B, how many branches do we have? So one branch here and one branch here. It has two branches. And the resistance of the two resistors are 24. So the bottom two resistors have a resistance of 8. Now we get everything between C and D, and from node D to B. And then we keep moving. Are there any other branches from C to B from another node? So we notice that there's a new node E over there. So we need this node E such that we can find the connection between C and E, then find the connection between E and B. So between C and E, we only have one branch over here. So that is 18K. Between E and B, there is one branch, which is 9K. Are there anything else that we didn't finish?
DE?
Yes, good catch. The only thing missing is over here. We haven't taken care of this resistor over there yet, so that is a 6K between D and E. Now we complete the equivalent circuit. Now the problem becomes, how do we simplify this network? We have to go through this one resistor. So the final answer should be greater than 24, right? Because it's 24 plus the rest. And for the rest of the network, we have this branch in parallel with the whole thing on the right-hand side. If we look closely on the right-hand side, we can simplify these two resistors pretty easily. We have two branches in parallel. And over here, these two branches in parallel. That's very easy. But over here, look, this is three resistors. I'm looking at these two as one resistor, one equivalent resistor. So 1, 2, and 3 resistors. And these three resistors form a delta-shaped network. So this is the delta-shaped network over here. And we need to replace that by the Y-shaped network. We can further simplify it, right? So before we do that, we want to simplify this portion first. So it has 224 in parallel, and the combination of that is 12 kilo ohm. So over here, that is 4 kilo ohm. To avoid me drawing another picture, I'm going to work on here. So remember, we already did the first step, simplification. I simplified these two resistors in parallel, and I make it 4 kilo ohm. And I did the same thing here, the total resistance for these two resistors, that becomes 12. So we already did the first step, simplify the two resistors in parallel. So the second step, we're going to use the Delta-wye transformation. In Delta-wye transformation, we're going to convert this delta-shaped network into the Y-shaped network. So we have a node C on the top, and we have a D and E over there. So we're going to still keep these three nodes. So remove all these three resistors, and we make it a Y-shaped network. So it's an inverted Y, right? The Y-shaped network looks like this. So we keep the top node C. There will be one resistor connected over here, and another resistor connected on the right-hand side. Then we connect this back to the original network. So let's call the first resistor RA. Let's call this RB, and I call the last one RC. Then we need to find out what is RA, RB, and RC. If we can find RA, RB, and RC, the simplification of this problem becomes very straightforward. The RA is connected to node C. It's equal to something
18.
divided by something else. The numerator, that is the multiplication of the two resistors connected to this node C. So we have a 12 and 18. So the denominator, that is a 12 plus 18 plus 6. So we can find RA that way. So look at the denominator. We have a 2 6. This is 3 6, and one more 6. So that is 6 times 6. We cancel the 1 6. Cancel another 6, it gives us a 6, and the final answer is a 6 kilo ohm. And similarly, we can find the resistance for RB and RC. So RB, because it is connected to node D, which is equal to the multiplication of the two resistors connected to node D. So over here we know that it's a 12 and a 6. So this is 12 times 6. So it's a 1/3 of RA, right? That gives us a 2 kilo ohm. And we can do the same thing for RC. RC, which is equal to the multiplication of the two resistors connected to node E divided by the total resistance. So that is 6 times 18. That'll give us half of that, which is a 3 kilo ohm. So that is how we calculate RA, RB, and RC. After we find RA, RB, and RC, we can calculate the total resistance RT. Looks like I'm going to run out of space. I'm just going to put the total calculation in one place then. Our total, that is 24 in series with the two bigger branches in parallel. So plus the first branch, that is a 9 and a 1 in series, and the second branch that has a RA in series with these two bigger branches in parallel. So that is RA. RA is a 6 plus RB plus 4 in parallel with RC plus 9. 2 plus 4, and the next branch over here are RC plus 9. RC is a 3 plus 9. So that is the final answer. That will give us the final answer. So let's see what the answer is. So I have 2 plus 4, that is 6. 6 in parallel with 12, that is 4. 4 plus 6, that is 10. 10 in parallel with 10, that's 5. 5 plus 24, that is 29 kilo ohm. Alright, so that's how we solve the problem. Next problem, we're going to find an I/O in the circuit. I/O is over here. So we see delta network. You can use this part as delta network. You can also see that this part is also delta network. The only difference is that now it's not a 3 resistors. We have 4 resistors, but these 2 resistors, they are in series. You can see them as one bigger resistor with a 6 ohm. By using the simplification, then you will see that 1 node, 2 node, 3 node, and between these 3 nodes you have 3 resistors that are connected hand by hand. This is delta-shaped network. Because we are looking for I/O, it's better to replace the top delta network so that we can keep this branch, right? Otherwise, we'll lose this I/O. We're gonna replace this part by a Y-shaped network. Let's draw the Y-shaped network then. I'm gonna copy this Y-shaped network, copy and put it over here. And I will connect this back to the original circuit. So now we have these 3 new resistors. We need to find out what are these 3 new resistors. So let's call them RA, RB, and RC. Then we can solve RA, RB, and RC, right? So look, in this problem, you have one branch that is 6, the other branch is 6, and the third branch is also 6. What is RA, RB, and RC? Do you remember? We had this on the quiz, right?
A third of it.
1/3 of a 6, so that is a 2 ohm. By looking at the network, we know the total voltage applied on the whole thing, that is a 26 volts. from here and here. And I have a complex network. I'm not sure like how to get the current over there. But I know that if I can find the overall current, say the current over here, if I can find the overall current there, and I will be able to find the current I/O down there, because these two branches are in parallel. So we can use the current division to help us to find the I/O. So then the problem becomes how to find this total current. To find the total current, I need the total resistance, so that I can use the Ohm's law to find the total current. Because I already know the voltage, that is 26 volts. And if I know the total resistance, I will be able to find the current, right? And in step 2, we're going to find the total resistance and the current. So the total resistance, let's use R. That is equal to 6 ohm in series with the rest. That will be plus. And over here, this is RA. RA is 2 ohm. Then we have, it's in series with these two branches in parallel. The first branch have a resistance of RB in series with this 6. RB is 2, and the other resistor is 6. On the right hand side, we have RC is 2, 3, 3. So that is 2 plus 3 plus 3. And after this, we have another resistor in series with them. So that is 6, so we plus 6. So that is how we find the total resistance. So let's see. This is 8 in parallel with 8, that is 4. 4 plus 6, 10. 10 plus 8. So we have 18 ohm. Now we can use the Ohm's law to find the current. And the voltage applied on the whole network, that is 36 volts. And the total resistance, that is 18 ohm. So we find it as 2 amp. After we find the overall current is 2 amp, we'll be able to find I/O. So step 3, we'll be able to find I/O by using the current division. So we know that I/O is part of this total current. And the ratio depends on the resistance in the two branches. This branch and the resistance in that branch. And the resistance in the right branch, that is RC plus 3 plus 3. So that is 8. The resistance on the left branch, that is 2 plus 6, that is also 8. So it means it's half of the total current. So that is equal to 1 amp. So next question. So this is a typical transistor amplifier is shown in this problem. We're going to find the amplification gain. So from one of the practice problems, we already learned that the amplification gain is a ratio of the output VO versus the input. And in this problem, the input is the VS. The circuit can be analyzed in two parts. So on the output side, and we have a dependent power source over here. This is a voltage source. And this voltage source depends on IB. IB is a current over here. So this IB makes a connection between the left and the right hand side. And if we look at the left hand side only, we'll be able to find IB by using all the information that we have from the left hand side. We're going to find IB first, then we find I/O. So step 1, find IB using current division, right? But I don't know the overall current. It's better for me to find the overall current so that I can use the current division. So let's first find out what is the overall current. Let's define the overall current as current I. And then we call this current I. And the total current I we can find by using Ohm's law, using the voltage applied on there divided by the total resistance. The voltage, that is 250 millivolts. So that is 0.25 volts. So that is equal to Vs over the total resistance. The Vs is equal to 0.25 volts. And the total resistance, that is the resistance for this network, which is 100 plus 5 in parallel with 500. 5K, 5,000 in parallel with 500. So that is how we find the total current. After we find the total current, we'll be able to find the current in this branch. The current in that branch, IB, that is equal to the resistance in the other branch, 5K, divided by the total resistance, 5,000 plus 500, times the total current, which is the current I. So this is how we can find IB. Once we find the current IB, we'll be able to find the output, right? If we know the current IB, we'll be able to know the total voltage applied on these two resistors. Pay attention to the sign, because over here, look at the bottom, that is the positive, and the upper side, that is the negative. So if we label the voltage applied on these two resistors, the voltage here as a positive and the voltage over there on the bottom as a negative, and we call this voltage as a V1. If we do that, V1 will be equal to negative 4 times 10 to the power 5 times IB. And then VO will be part of V1. So find VO using the voltage division. So VO is equal to 300 over the total resistance, which is a 4K and a 300. So that is 4,000 plus 300 times the total voltage, which is V1. So this is how we find a VO. Once we find a VO, the amplification gain is equal to VO over VS. If you want to keep VS as a variable, you can do that as well. So the amplification gain is G is equal to VO over VS. So let's look at the last example. If the power absorbed by this 10 volt source is 40 watts, calculate IS. So IS is over here. In this problem, it also have a dependent source as well. This is a voltage source and it depends on Vx. If you find that the problem is more complex than you can think of any solutions, my suggestion would be do it little by little. So let's try to see what we can find from the given information. Given this information 40 watts, I will be able to calculate this current. And pay attention, we need to use the passive sign convention to define this current. So let's call this current I1 then. Find this current I1 by using the power divided by the voltage. So that is a 4 amp. Because the passive sign convention, on the top that is a positive, on the bottom that is a negative, and the current flow from the higher voltage end to the lower voltage end, so that it will match the passive sign convention. I will be able to find the voltage on this resistor. So I'm going to call that a V1. I can find a V1 by using Ohm's law. V1 that is equal to current I1 times the resistance 5 ohm. So that gives us 20 volts. So we find the voltage drop on that, which is nice, which gives us Vx. The Vx is equal to the voltage drop from this node to that node, which is equal to V1 plus 10. So Vx is equal to V1 plus 10. So this is the way we use the definition of a voltage to find Vx. Of course, you can also use KVL by writing the KVL equation. We count the voltage drop from here V1 plus 10, then minus Vx that is equal to 0, which will give you the same answer. So we find that as 30 volts. So I'm going to call that voltage as V2.
Professor, I had a question.
Yes.
For V1, is there a reason why you put the positive side to the left of it?
Yes, because because I'm trying to use the current I1. The current I1 flow from the left to the right. This is why, to make it compatible with the passive sign convention, I have to define it this way.
Okay, thank you.
So now we define V2. So V2 is the same as this 0.6 Vx. 0.6 Vx, so that is 18 volts. Once I find a V2, I notice that I can find the current in this branch. And if you want to find the current, you can define the current flowing downward so that it will be compatible with the passive sign convention, right? So I know my current I2 as well. So I can find I2 by using Ohm's law, which is V2 divided by 10. So that is 1.8. I found a lot of information already. Now look at the problem again. I'm looking for the current IS. So I know the current in this branch. I know the current in this branch. If I know the current in these two branches, then the problem will be solved, right? Then I want to know what is the current in this branch. So let's define that current as well. So let's call that a current I3. The current in this branch that can be found by using Vx divided by 15. So let's call this current I4. So I can find the current I4 by using Ohm's law, which is equal to Vx divided by the resistance 15. That is 30 divided by 15, so that's 2M. Then we can find I3 by using KCL, right? I3, the current goes into the node that will be split into two branches. The current into the node is equal to the current leaving the node. So that is equal to I4 plus I1. 4 plus 2, 6 amp. So half of the problem is solved. I know the current in this branch. I don't know the current in this branch. If I know the voltage drop, then I'll be able to do that. I will define this as my voltage V3. And the current, let's call it I5. Now we define everything, almost everything. Like we have a lot of information on the circuit already. To find out V3, so let's call this total voltage drop as V4. So we know that V4 can be calculated by using this branch, and V4 can be also calculated by using that branch. If we calculate V4 by using the right-hand side, which is equal to the voltage drop on this 4 ohm resistor, which is 4 times I3. I3 is equal to 6 amp, so I'm going to plug in the value directly, plus Vx. So Vx, that is 30. So 30 plus 24, that is 54 volts. And at the same time, V4 is equal to V3 plus V2. So this is from the definition with the voltage drop V4 is equal to the voltage drop here plus voltage drop there. And it's also equal to voltage drop over here plus another voltage drop. Then we can find a V3. 54 minus 18, that will give us 36 volts. Once we find a V3, we will be able to find I5 by using Ohm's law. I5, that is equal to V3 divided by 6. That is 6 amp. Now the problem is clear. So we have one current source, IS is something I'm looking for. So the current goes into the node is equal to the current leaving the node. So we can find IS by using KCL, which is equal to I3 plus I5. So I5 is 6, I3 is 6, so that in total is 12 amp. So look at this problem. I'm going to find VAB. So to find a voltage, we have two different ways to do that. We can find a VAB by using definition, or we can use a KVL. So I'm going to define this loop. I write a KCL equation. What do I have? Apply KVL to loop 1. So the voltage of VAB is from here to here. So I find VAB. So VAB plus the voltage drop on this 10 ohm. I'm not sure what this voltage drop on this 10 ohm is. At the same time, I don't know the current in this 10 ohm resistor, right? So I'm not sure. I'm going to define my voltage drop here. So let's call this voltage drop V1. So you can totally define it in the other way. If I define it in the other way, I will have a minus sign over there. So I don't know here, but I'm going to just define it that way. Here, I'm going to call this voltage drop V2, and I'm going to put the left-hand side positive and the right-hand side negative, because I want to use a positive V2 over here as well. So that I will write my equation as, according to my reference, this will be V1 plus V2. That will be equal to 0. So if I find a V1 and a V2, the problem will be solved. But I don't know how to find a V1. V1 is the voltage drop on this 10 ohm resistor, but I don't know. If I know the current, then the problem will be solved, right? So let's see how we find the current in this branch. And the same thing for V2. If we know the current in this branch, then the problem will be solved, right? So look at the circuit. It has two branches in parallel. One branch and the second branch, they're in parallel. You also know the total current. It means that we can find the current in each branch. So assume that this is our current I1. Let's call this current I2 then. So how do we find the current I1 and I2? So we'll find the current I1 and I2 using current division. So this requires you to remember the conclusion that we did before. So the current I1 is the current in this branch, and the overall current is defined this way. The current in this branch is equal to the resistance in the other branch, which is 10 plus 15, which is 25. Let's just write it as 25 then. Divided by total resistance, the resistance on the top branch, that is 10 plus 5, that is 15. So 15 plus the other branch is 25, times the total current, which is 4. So this will give us 4 divided by 40 is 0.1, so that is 1.5 amp, right? So this is how we find I1. And we'll do the same thing for I2. You can use a similar equation to find I2, or you can also use KCL to find I2, because I know the current goes into the node, that is equal to the current leaving the node. I2, that will be equal to 4 minus 1.5, that will give us 2.5 amp. After you find I1 and I2, you'll be able to find a V1 and V2 by using Ohm's law. Find V1 and V2. You just need to pay attention to the signs because we didn't really try to define them by following the passive sign convention. So V1 is defined positively on the right hand side, but the current I1 is defined in the other way. If you want to make it be compatible with the passive sign convention, the current should be from the positive end to the negative end. So this is why we use a negative I1 times 10. Negative 1.5 times 10, that is a negative 15. So this is how we find out V1. And we can find a V2 by using Ohm's law again. So V2 is equal to current I2 times 10. So I2 is 2.5 times 10 ohm, that is equal to 25 volts. So that's how we find V1 and V2. After we get all this, we'll be able to find a conclusion. VAB is equal to negative V1 minus V2, right? So that is 15 minus 25, so that is a negative 10. So that's how we solve this problem.